basically, as we saw, that if x1 greater than x2, then discard x2 because the median will be in x1. So basically, at each step we divide the array into x1 and x2 as our previous definition, where we saw that x1 equal to x such that x belongs to capital X and x such that x strictly less than a, where a was our splitter and x2 was x minus x1. Okay, this was our definition of x1 and x2, and if we see that the sizes of both of these is n by 2 in the first iteration, then we have a as our median. If not, then will recurs, and what we'll do is that will discard the smaller set, because suppose if x1 is greater than x2, then discard x2. Okay, because our median is in the x1 set. So now we have a smaller array. Say the size of x1 is k, size of x2 is n minus k, and this is greater, and we have to look for the nth element in this array, n by 2th element in this array, not the k by 2th element. So in our next recursion we also have to send this number n by 2th, and in that split of x1, which will be the x in that next recursion, we'll split x1 into, again, x1 will become the x, and we'll split this array into x1 and x2, and we have to find the n by 2th element in that splitting. So recursively we'll look into that, where this n by 2th number will go, and the other part of the array we will discard. So at each iteration we are not looking into a part of the array, and so it should be order of n. Only if we don't spend any order n time, more than order n time, like we don't spend some order n time in finding out the splitter. Okay, because we are doing while one and checking if a is a good splitter. Okay, so if this takes order of n time, then our algorithm would be each step would be order n square, because at each step, if this while one runs for order n time, and we are finding out, and then after that we are doing a check of that. So basically, if that takes order n squared time or n to the n time, then our algorithm would not be order n time, so it should not exceed order n time. So basically we'll have to find out it should not be exponential time or so. So what we need to do is check how long will this probabilistic part take. So basically we need to find the estimate. So we saw that if we take the sorted permutation of these n numbers, then basically we're looking at the middle n by 2 elements, and those are my good splitters. So basically probability of selecting of getting a good splitter is basically if we select one of those elements, of those n by 2 elements. So basically the probability is half. So the estimated number of times, number of trials would be 1 by p. So basically 2 times. In 2 trials we are supposed to get a good splitter. So basically our algorithm will then be linear time, because in 2 trials we get a good splitter. In expected 2 trials, in expected linear time, okay, so in expected 2 trials or expected 1 by p trials, we are getting success, that is we are getting a good splitter. And then after that, in order n time, we are distributing x into x1 and x2 like I have told in my previous video. And so after that we can look for the n by 2th element in the bigger array if it's x1, and if x1 is bigger, and if x1 is smaller, then suppose x1 is smaller, then here we have to look for the n by 2. So this is n by, not the n by 2th element, so this is basically n by 2 minus k. Okay, n by 2, this is n by 2, this is my k, so n by 2 minus k. So n by 2 minus k is basically this n area. So basically n by 2 minus kth element in x2 if x2 is of size n minus k. Okay, and n minus k is greater than k. In that case we have to look for the n by 2 minus kth element in x2 to find the median. Okay, so that's it for my median finding, probabilistic median finding algorithm. So we now go into an easier algorithm, which is basically finding the second maximum algorithm. Basically, suppose we directly take an example how this algorithm works, and that's how you need to check it. Suppose we have this 1 2 3 4 5 6 7 8 numbers. Let's do with these 8 numbers, and we need to find say suppose we are looking for the second maximum. So okay, so basically we need to what we are doing is finding out using a tournament tree. Construct a tournament tree, which is actually a binary tree, which at each steps finds out which is the maximum among its 2 leaves and pushes that up. Okay, and like that we'll build the tree. So among 5 and 10 the maximum is 10, among 20 and 8 the maximum is 20, among 16 and 56 maximum is 56, 1 and 12 the maximum is 12. So among 10 and 20 maximum is 20, 56 and 12 maximum is 56, among 20 and 56 maximum is 56. So we got our maximum. So if while building the tree we get our maximum, and so the number of comparisons we are making is order of n, obviously, because so see at each step here we have n by 2 comparisons, here we are making n by 4 comparisons, so as to ultimately get 1 comparison. So basically if we have n numbers, the number of comparisons we make while building the tree is basically n by 2 plus n by 4 plus up to 1, which is less than equal to n minus 1, which is basically the total number of nodes of the tree. So you can sum it up and check. Okay, so that's actually n minus 1. So now what we need to do, so where is my second maximum? So second maximum is somewhere where it must have it must have lost to 56 somewhere. Okay, so basically we have to check for all numbers that have lost to 56 somewhere, right? So basically the second maximum will be this number, because this number is the largest among all these numbers, right? So second maximum is either this number or the number which has lost to 56 somewhere, right? So basically this number has also lost to 56. So basically all numbers which have lost to 56, we have to check. So basically at each level 56 must have 1 because it's the largest number. So basically all numbers which have lost to 56, like say 20, 12 and 16, the maximum of those is basically my second maximum. Okay, so if suppose just exchange 20 and 12, so basically if 20 was here, 12 was here, second maximum was not here. Okay, so basically it's not the left number or the number which lost to 56 in the final stage. Is we have to check where it lost to 50, all numbers which have lost to 56. So basically we have to go to the height of the tree, right? We have to go to the height of the tree. So basically our height of the tree is a ceiling of log n. Okay, ceiling of log n. And so basically number of comparisons to find the maximum among this is again linear time. So basically order of log n, ceiling of log n minus 1. So maximum among this all numbers that lost to maximum is ceiling of log n. To look at those is ceiling of log n, and to those numbers to find the maximum among those is log or ceiling of log n, so minus 1. So basically the total time required to find the second maximum is actually order of n, but it's n minus 1 for to build the tree, plus log of n, ceiling of log n minus 1. So basically n plus ceiling of log n minus 2. It's an interview question, basic interview question, okay, often asked. So that's it. Okay, so again one more thing I want to say is that so this was our median finding algorithm for this. Now we also have another median finding algorithm in which we actually divide it into suppose q subsets, right, like five element subsets, so n by 5 such subsets, and then do a median of medians algorithm to find the kth largest number or the median. So in the median algorithm also you saw that in the next iteration we are not looking for the median in that array. So basically this is a rank finding algorithm, so we need not find the n by 2th ranked element. We can find any ranked element using that algorithm of the median finding algorithm. Similarly, the next median finding algorithm that we are going to study in a later chapter will be that. So now we'll be doing sorting. Okay, sorting. We'll be doing sorting in our next class.